Hello! Today we're going to explore a fundamental concept in multivariable calculus, partial derivatives. By the end of this video, you will be able to define a partial derivative, understand its geometric meaning, and calculate partial derivatives for various functions. You're already familiar with the derivative from single variable calculus. It tells us the rate of change of a function with respect to its single input variable. For a function y equals f of x, the derivative dy dx gives us the slope of the tangent line at any point on the curve. But what happens when a function has more than one input variable? For example, a function z equals f of x comma y. This function represents a surface in three-dimensional space. How do we find its rate of change? The problem is, the rate of change depends on the direction we're moving on the surface. We can't just find the slope. This is where partial derivatives come in. They allow us to find the rate of change in a specific, simple direction. Let's visualize this. Imagine our surface z equals f of x comma y. If we want to find the rate of change with respect to x, we can hold the y value constant. This is like slicing the surface with a plane parallel to the xz plane. The intersection of the plane and the surface is a curve. This curve is a function of x only, since y is fixed. We can then find the slope of the tangent line to this curve. This slope is the partial derivative of f with respect to x. Similarly, if we want the rate of change with respect to y, we hold the x value constant. This is like slicing the surface with a plane parallel to the yz plane. The intersection is a curve that is a function of y only. The slope of the tangent line to this new curve is the partial derivative of f with respect to y. So a partial derivative is just a regular derivative, but we treat all other variables as constants. It tells us the slope of the surface in a direction parallel to one of the coordinate axes. Now let's talk about notation. There are several ways to write partial derivatives. The most common notation uses a curly, d, called eta, del, copo. So, the partial derivative of f with respect to x is written as del f over del x. You might also see it written as f with a subscript x, or f sub x. This is a more compact notation, especially when dealing with higher order derivatives. Similarly, for the partial derivative with respect to y, we have del f over del y, or f sub y. These notations all mean the same thing. Find the derivative of the function f, treating y as a constant. Let's formalize this with a definition. The partial derivative of f with respect to x is defined using a limit, just like a regular derivative. It's the limit as h approaches 0 of f of x plus h comma y minus f of x comma y all over h. Notice that the y value remains constant throughout this limit. The definition for the partial derivative with respect to y is analogous. It's the limit as h approaches 0 of f of x comma y plus h minus f of x comma y all over h. Here, the x value is held constant. Now for the best part, calculating them. The process is surprisingly straightforward. To find the partial derivative of f with respect to x, you simply treat y as a constant and differentiate the function with respect to x using all the rules you already know. Let's try an example. Find the partial derivatives of the function f of x, comma y equals x squared y plus 3x. First, let's find the partial derivative with respect to x, or f sub x. We treat y as a constant, so the derivative of x squared y is y times the derivative of x squared, which is 2x. The derivative of 3x is just 3. So f sub x equals 2xy plus 3. Now let's find the partial derivative with respect to y, or f sub y. This time, we treat x as a constant. The derivative of x squared y is x squared times the derivative of y, which is 1. The derivative of 3x is 0, because x is a constant. So f sub y equals x squared. Let's do another one. Find the partial derivatives of f of x comma y equals e to the power of x times y. For f sub x, we treat y as a constant. Using the chain rule, the derivative of e to the u is e to the u times the derivative of u. Here, u is xy, so its derivative with respect to x is y. This gives us y times e to the xy. For f sub y, we treat x as a constant. The derivative of xy with respect to y is x. So f sub y is x times e to the xy. Just like with single variable derivatives, we can find higher order partial derivatives. This means we can differentiate a partial derivative. For a function of two variables, there are 4 second-order partial derivatives. First, we can differentiate with respect to x twice. This is written as del squared f over del x squared, or f sub x. This means we find the partial derivative with respect to x, and then we differentiate that result with respect to x again. Second, we can differentiate with respect to y twice. This is del squared f over del y squared, or f sub y. This means we find the partial derivative with respect to y, and then differentiate that result with respect to y again. The other two are called mixed partial derivatives. We differentiate with respect to one variable, and then the other. The notation del squared f over del y del x means we differentiate with respect to x first, and then with respect to y. The subscript notation f sub xy means the same thing. And del squared f over del x del y, or f sub yx, means we differentiate with respect to y first, and then with respect to x. A remarkable result, known as Clairaut's theorem, states that for most functions you'll encounter, the mixed partial derivatives are equal. That is, f sub xy equals f sub yx. The order of differentiation doesn't matter. This can save you a lot of work. Let's put this into practice with an example. Let's find all 4 second-order partial derivatives for the function f of x, y equals x cubed y squared minus 2y. First, we need the first-order partial derivatives. F sub x is 3x squared, y squared. F sub y is 2, x cubed y minus 2. Now for the second-order derivatives. Let's start with f sub x, x. We differentiate f sub x with respect to x. The derivative of 3x squared y squared with respect to x is 6x y squared. Next, f sub y. We differentiate f sub y with respect to y. The derivative of 2x cubed y minus 2 with respect to y is 2x cubed. Now for the mixed partials. Let's find f sub xy. We differentiate f sub x with respect to y. The derivative of 3x squared y squared with respect to y is 6x squared y. And finally, f sub yx. We differentiate f sub y with respect to x. The derivative of 2x cubed y minus 2 with respect to x is 6x squared y. Notice that f sub xy equals f sub yx, just as Clairaut's theorem predicted. This is a great way to check your work. Partial derivatives are not just for functions of two variables. The concept extends to any number of variables. For a function w equals f of x, y, z, we can find 3 first-order partial derivatives, f sub x, f sub y, and f sub z. The rule is the same. To find the partial derivative with respect to one variable, you treat all other variables as constants. Let's find the partial derivatives of f of x, y, z equals x squared y plus yz cubed. For f sub x, we treat y and z as constants. The derivative is 2xy. For f sub y, we treat x and z as constants. The derivative is x squared plus z cubed. For f sub z, we treat x and y as constants. The derivative is 3yz squared. The same logic applies to functions with 4, 5, or any number of variables. The process remains the same. Let's quickly recap what we've learned today. We started by defining a partial derivative as the rate of change of a multivariable function with respect to one variable, while holding all others constant. Geometrically, it represents the slope of the surface in a direction parallel to a coordinate axis. We learned the notation, like del f over del x or f sub x. And most importantly, we saw that to calculate a partial derivative, you simply treat all other variables as constants and differentiate. Finally, we explored higher-order derivatives and the powerful Clairaut's theorem, which states that for most functions, the order of mixed partial differentiation doesn't matter. Partial derivatives are a cornerstone of multivariable calculus and are essential for understanding concepts like tangent planes, optimization, and vector fields. Keep practicing, and you'll master them in no time. Thank you for watching.